I'm Brett Denevi. I work here at Johns Hopkins Applied Physics Laboratory. My background is in geology and planetary geology. I'm the deputy PI for the Lunar Reconnaissance Orbiter cameras, currently orbiting the moon. And I worked on the Messenger mission. I still do. Messenger obviously ended about a year ago, but we're continuing to work on it, get all the data assessed, put into the public, the Planetary Data System archive so that everyone can use it, and just finishing up our, some of our science analysis from the mission. Messenger was conceived as kind of a follow-up mission to Mariner 10. Mariner 10 flew by Mercury 3 times in 1974, 1975. This is just a map showing it saw about half of the planet. Saw half the planet. So Messenger's job was really to kind of complete our reconnaissance of Mercury. We didn't know what was on the other side of the planet. We didn't know what Mercury was made of. We didn't know why it had such a huge core. And so this is what the goal was, and what we achieved from Messenger is global coverage in both, monochrome images, so we could look at the geology, color, topography, compositional information, gravity information, and multispectral information. Achieving all of this was really difficult. One of the hardest things is just dealing with the Mercury environment. You heard a little bit about how at Pluto it's such a challenge to have enough power. So this is Messenger when it was being built here at APL. And we have the opposite problem. We have too much sunlight. It's too hot. So around a third of the solar panels that you see folded up there are actually mirrors, to just get rid of some of that excess sunlight that we don't need, keep the spacecraft from getting so hot. And then the other aspect of that was really necessary to keep the spacecraft cool was the sunshade on Messenger. You can see it's this white area here, and that was made of ceramic cloth. And so that was this sunshade that basically always had to point at the sun. We couldn't move more than 12 degrees in any direction away from the sun, or the spacecraft would get too hot. The instruments could be damaged. And so that was a really interesting constraint actually for the whole mission. You can imagine having to always kind of keep your back to the sun in that way. And then another way we dealt with the heat there is with the orbit. So the sun is hot, but Mercury is also extremely hot. So staying too low over the surface for too long would essentially bake the spacecraft from the other side. And so the way that Messenger dealt with that problem was with a really highly elliptical orbit. So the orbit at the closest point was around 200 kilometers from the surface. At its farthest point, it was 15,000 kilometers from the surface. And that was just to allow that long period of time to cool off before you came around again close. And so I worked on the camera team for Messenger. And you can imagine this was an interesting challenge too, because we wanted to get global coverage with, more or less the same resolution. So we could kind of get a global map, global imaging to understand Mercury's geology. And so the way we had to deal with this was with 2 cameras, one that was very high resolution, and for our global imaging, we used that mainly when we were very far away from the planet. And then when we were up close to the planet, we had a lower resolution camera. You might ask, why don't you want high resolution all of the time? Why not just keep taking high resolution images? Well, the problem is then you get these very tiny little postage stamps of the surface. So the lower resolution camera that we used when we were up close, it had a wider field of view. You could start getting a bigger picture. Otherwise, we never would have been able to get global coverage across the surface. And the other reason, too, is that we had a lot of data volume problems. Images, one image is not a huge thing, but you start adding these all up. There was a limited amount of onboard storage to save these up, and the reason for that too is that there's only a limited amount of time you have to downlink images. You have to point the spacecraft towards the antennas on Earth, use the Deep Space Network, and the Deep Space Network is actually very popular. Everybody wants to be sending their images down to Earth. So we had to kind of compete for time. So we had limited amount of time, so limited amount of volumes we could send back to Earth. And so I was on the camera team. Our job was to get as many images of the surface as we can, get high resolution images, but we also had to balance that with what other instruments on the spacecraft wanted to do in terms of their data collection strategies too. So I think what I put next is just a few examples of some of the really amazing images, things that we saw on Mercury. So we did, for select targeted areas, get very high resolution, beautiful images. This is an example of that for a crater called Aberdeen in Mercury's northern hemisphere, the only places that we could get truly high resolution images. You can see the central peaks of that crater. This is a volcanic vent. So the bottom part is a hole in the ground here. This was caused by a big explosive eruption. One of the things exciting about Mercury, we thought there wouldn't be a lot of gases and volatiles on the planet to drive explosive eruptions, but we were wrong. There's tons of explosive volcanic events that happened in Mercury's history. This is Cortez crater. This is showing on the floor, you can see kind of an unusual texture, unusual pattern there. If you go to the next slide too, I put a couple of these because they're so beautiful. You can see this kind of etched terrain where these are actually made up of minerals that are not stable over the long term on Mercury's surface. So they're essentially subliming, eroding away. Another thing we didn't expect to see. And then just another example of that. Same thing, you can see the blue areas are the areas that are made up of these hollows where we have volatile rich material not stable on Mercury's surface. And then in the overview at the beginning, they mentioned a little bit about the permanently shadowed regions on Mercury. So these areas in yellow are areas where we have permanent shadow, and then those areas are filled with water ice deposits. And this is a really fascinating story too, because everywhere you have permanent shadow on Mercury, areas that will never see sunlight, you have these ice-rich deposits. Probably not what you think of when you think of the planet Mercury, but the moon also has permanent shadows, and it has a little bit of ice, but not anything close to what you see here on Mercury. So that's been one of the really interesting kind of comparisons to look at. Why doesn't the moon have these kinds of ice-rich deposits? Why is Mercury such an interesting case? One of the ideas is that there was a recent cometary impact on Mercury, and that ice was deposited water molecules that migrated to the poles from that kind of impact. I think that's all the slides I had too, so I was hoping to take any questions you guys had about Messenger, Mercury. Yeah, go ahead. All right, so the question was, how was the water detected in the shadowed areas, which is really fascinating story, actually. So the earliest detections of this water ice came from Earth-based radar observations. And so they could tell there was some kind of unusual material in the poles. Messenger was sent to, in part, to follow up on that observation. So we sent a whole array of ways to look at that. One was through a neutron spectrometer that can detect enhancements in neutron absorption, which are usually due to water. So we saw that. There's a laser altimeter. It's usually used for measuring topography, but you can also use it, you bounce a laser off, see how bright the material or the light is when it comes back. So that was very reflective in the poles, consistent with water ice. And then my favorite part, because I worked on the cameras, was from the imaging. We actually worked really hard to be able to take images of these areas that are in permanent shadow. And the way we did that is using sunlight that scatters off of crater walls, So you have just a tiny bit of light, and then you can take a very long exposure image with our most sensitive filter, and we actually imaged the water ice deposits on the surface. Yeah, go ahead.
Did you say that the water ice moves to the poles? How does that happen?
Yeah, that's kind of an interesting problem that's hard to wrap your head around. But it's basically, I think the general idea is that you have basically kind of maybe even a temporary atmosphere that forms after a big cometary impact. But you have all these water molecules that are not stable anywhere where there's sunlight. And so they're kind of hopping around until eventually they kind of cold trap. They get trapped in cold areas and build up there. Obviously, lots of it is lost to space, but enough of it migrates until it gets stuck in a cold spot. All right, a question from JSC. Did you get any information about the atmosphere when it impacted? I think that must be referring to Mercury's atmosphere. Mercury does not have an atmosphere, but it has a very tenuous exosphere, which is basically you could fit all of Mercury's so-called atmosphere into a suitcase because it's so hot there. Not a very high gravity body. You don't have a very strong atmosphere. We did get a lot of information about what kind of molecules were in the atmosphere, exosphere of Mercury, sodium. We think that you can actually see potentially like a Northern Lights aurora in Mercury from this kind of sodium glow. And we did image that too, actually. But that was all collected before impact because we did not have the antennas pointed at Earth. There was no way to send any more data back after impact, so that was kind of almost in the blind. Yes?
Well, let's kind of shift into a lot of this, but in the beginning you were talking about how they're preparing the spacecraft for the heat, etc.
Mm-hmm.
You mentioned the ceramic cloth. Just out of curiosity, is the ceramic cloth they use something that's used in other industries already, or did they have to create it for this? And if so, what are the spin-offs that it's used?
So the question was about the ceramic cloth, and it is a great question, but I don't know the specifics of how it was used. I mean, these kinds of ceramics are, very popular for shielding from heat, in part because they do such a good job, also because they're so lightweight. I think the one designed for Messenger was unique to Messenger, at least at that time, because it needed to be so light. It was very hard to get the spacecraft to Mercury and into orbit. So much of the mass of the spacecraft was actually taken up with fuel. And so everything else just had to be squeezed down, shave off every little ounce. So that's why it was, a very thin cloth rather than some kind of bigger shield. Thank you.
Thank you so much, Brett. It's fabulous. It's fabulous.